Good morning, everyone, and welcome to this volcano session. So I'm Virginie Pinel from IRD, working at ISTER, and I'm currently speaking from Chambéry in France. And I have the pleasure of co-chairing this session today, together with Susie Meyer from University of Leeds. So we will have 5 talks and then the questions. So please ask and post your questions on a Slido. And in case we will have time after each talk, we will take questions. Otherwise, we will have the question at the end. So first, we will move to I will give I will let it to Paul Lundgren, who is the first speaker. And so Paul is at GPL, and he will talk today about the dynamics of large silicic systems from satellite remote sensing observations, the case of Domio Volcano, Argentina. So Paul, it's yours.
Okay, thank you. Let me can you see my slide?
Yeah, perfect.
Oh, okay, great. All right. Good morning. So today I'm going to talk about an intriguing volcano in Argentina called Domullo that we kind of happened upon a few years ago. And this work's been done with Tarsila Girona, Grace Bato, Vince Realmuto, Sergei Samsonov, Carlos Cardona, and Luis Franco in Chile, Eric Corolla, Michael Ibas, JPL, and Fabio Pulverenti, and as well as some recent modeling work with Kurt Feigl at University of Wisconsin. So as I mentioned, this is a volcano that's found somewhat serendipitously because we were looking for, at the request of the Chileans, we were looking for activity at where my cursor is, if you can see it, at Nevada State Chillán. And this is ALOS 2 data, and instead what we found is, of course, well-known Laguna del Maule, but about 65 kilometers south of there, we found this other signal that turns out to be a volcano called Domullo. And the intriguing thing with Domullo, so again, here it is in South America, and Laguna del Maule is here in terms of seismicity, and Domullo is down here. And if we zoom in on that, Domullo, it turns out, is a rather odd volcano because it hasn't erupted in 100,000 years, and it has both rhyolitic flows that are most active to the southwest, as well as a rhyolitic core to it, and yet it has draped over it. It has Mesozoic marine sediments that dip outward. So it's as though you have this some kind of deep dome growth with activity that's been growing from beneath. So it's rather, and I should point out that just to summarize here, it's also been found to have the second largest hydrothermal energy release after Yellowstone in the world. It has a high heat flux, and which is hard to explain if the most recent activity was 100,000 years ago. So most of the literature on this up until recently has only been based on, is very little literature, and it's based on the geothermal activity or geothermal potential. So as I mentioned, this volcano, we found it with ALOS 2 data, and this just shows some 3-year interferograms. So these were up until 2018 from 2015. So over 3 years, we saw significant deformation from both descending and ascending tracks. So you can, of course, clearly see based on the skewing, the skewing of the deformation towards the satellite look direction, that of course it's consistent with some kind of pressure source at some depth. So nothing, it's very fairly generic in that sense. And then, so that was ALOS 2 data. So we were seeing that it was inflating at a significant rate. And what was intriguing then was to try to go back in time and say, well, when did this start? At first, we thought it might have been something triggered by the Maule earthquake or something like that. So we didn't really know. So we went back and we looked at ALOS data, and what we found, in fact, was that, again, if you look at a 3-year interferogram from ALOS, we see Laguna del Maule, of course, deforming quite rapidly in those days. But we also found that a signal at Demuya, but it turns out this, in fact, was in deflation, it was the opposite sign. So that made things a little bit more interesting. And in fact, what this is just a summary of some individual interferograms, but the key thing is that, and these are all inflation signatures from over different times. Some of these are annual pairs, and some of these are multi-year pairs from both ALOS 2 and Sentinel. But when we look back at some RADARSAT 2 data that Sergei Samsonov processed, we found that from 2013 to 14, in fact, it was null. So we had deflation from 2008 to 11, null deformation in this year. But then from early 2014 to very early 2015, we started to see inflation emerge. And so then we did some SAR time series analysis. I won't go into it. Basically, at the time, we used Giant. More recently, we're using MintPy. And so this is kind of a summary slide. This is from a paper we published in last year in Scientific Reports. And there's a couple of, so I mentioned the deformation time series shown here from various satellites. There's some ambiguity in terms of whether the ALOS deflation, did it go to zero here with a long repose time, or did it magically kind of go to zero just in 2013 when we see the RADARSAT 2 null deformation, which then turns the corner here. And then, of course, all Sentinel and ALOS 2 time series from various tracks showed a strong, roughly linear trend of stronger inflation. And so now, one of the key areas of interest in this volcano, or intriguing things that we found, was that Tarsila Girona at the time was just developing his thermal time series method to get to quantify kind of a thermal energy release for the entire volcano edifice. And he has since published that in Nature Geoscience this past March for a number of other volcanoes. And the key thing here that was intriguing was that we see this thermal signature that looked very much, has a similar shape to the deformation. And yet, when we did some cross-correlation analysis, which is quite limited for signals of this length, but the question is does the thermal signature, the first impression might be, well, it lags behind the geodetic signature, but it could also be anti-correlated and actually be ahead of the geodetic signature. So, and then at the bottom, I also show the seismicity, which was increasing at least into 2019. It was increasing dramatically at the time, it appears. So there's a lot of concern from both the Chileans and Argentinians about this volcano. Since it had the potential, it was thought, for potentially large eruption. So we did the first thing we did was some source analysis based on the mean linear velocities of the ALOS 2 data. And we used the catnip algorithm implemented in Altar for a CDM source, which is published by meeting the coup in 2017. So we use this Bayesian approach to estimate the parameters. And the key thing that we find is a source that's at about 6.5 kilometers, relatively tabular. And these are the main thing I want to show you is that the volume change rate is over 37 million cubic meters per year, which is actually higher than has been estimated for Laguna del Male. So even though the deformation is less than Laguna del Male, because it's deeper and larger source, the volume change is actually a little bit greater, comparable. So I'm not going to spend too much time on the fit to the data, but nonetheless, this is what we find from some different views. The summit is right here. So roughly tabular source. And the thing that was interesting is that the seismicity was all around kind of in an annulus, mostly to the west and southwest. And if you recall, the southwest is where the geothermal activity is concentrated. So it kind of fits with that. In terms of the source, one of the things we did was we used Tim Davis's cut and displace boundary element code to take that CDM solution, convert it to an ellipsoid, and calculate what the dilational strain would be. And what we found was that it, of course, ended up being consistent. It's a little bit hard to see here because you need to rotate it, but basically even the ones that are in the blue turn out to be outside and in the red zone where you would expect fluid circulation might be enhanced due to the inflation. So it seemed to be kind of consistent with a kind of cartoon model where fluids or gas percolate from a deeper source. And based on those cross correlations, the question really was, whether is this, if the geodesy signal precedes the thermal signature, that would imply most likely some kind of bottom-up magma influx. That then our hypothesis is that a new batch of magma comes into the system, degasses, and diffusion of gas reaches the surface, gives off excess heat, latent heat as it condenses, and then that, of course, gives us this thermal signature. So the time lag is related to the diffusivity and the permeability and porosity of the medium. And you can, of course, there are a wide range of plausible values, and a couple of years of delay it would not be unexpected. And so, and this again is more on the conceptual model. And so in addition, Tarsila Girona in 2015 had a paper in which they posited that in an open system, you could have a case where passive degassing would lead to decompression at the top of a conduit going to a deeper reservoir, and that would give you this kind of signature. And when we saw that, it was intriguing because it basically looks like the geodetic signature at Demullo to first order. And in fact, our question is whether you could have a similar model, but for a closed system that would do something similar, so that degassing would unload the base of this and a conduit to deeper reservoir would open that would lead to pressure reequilibration, and so rapid inflation that would then flatten out. And at the time that we were doing this, we were in a pretty much linear phase. So we didn't know if this might be the case, and we still haven't really done the modeling to see how plausible that might be. And that's work we're currently doing. However, so part of the ongoing work, one of our first steps is to implement a model using COMSOL, a multi-physics model that has a thermal temperature regime, so temperature-dependent viscosity for the medium around a a simple conduit into a ellipsoidal reservoir at the depth and dimensions of the DeMuyo source. And we can play with some, for some simple forward modeling that I just did for the SAR inflation from one of the Sentinel-1 time series going up through about a month ago for a point, for a model point that's located at the top. So it's not really, we haven't done this for the full 3D case, but what you can find is for some reasonable set of values. Yep.
You would have 1 minute left, please.
Good, perfect. So for some reasonable values, you can fit this signal, and the fact that this is now rolling over is intriguing because it seems to be fitting our initial kind of model. And so just to conclude, DeMuyo is this active but kind of enigmatic volcanic system, but it's a rhyolitic system, so it has a potential for a large explosivity. And we found this source at 6.5 kilometers depth with a large influx rate. And there's about this 4-year lag between thermal and INSAR, we think. And so we think, a gas diffusion model might be explaining this rather than considering this as a volcano that's just about to, might be erupting. We think it's based on its past behavior or lack of eruption in 100,000 years, it's probably been doing some kind of behavior like this for a long time. And therefore, it's really much more akin to a restless caldera, such as Yellowstone, Campi Flegrei, or maybe Laguna del Maule. And so we want to better understand this by developing improved physics-based models. Thank you.
Thank you, Paul. So I think we will move to the next speaker, which will be introduced by Susie.
Thank you. So our next talk comes from Federico Galetto, and he's going to talk about eruptive unrest at Cerro Azul in the Galapagos.
Hi, thank you. Can you see my screen now? So, good morning to everybody. I am Federico, and today I will speak about the 2008 eruptive arrest at the Cerro Azul volcano, revealed by insert data and a novel method for geodetic modeling. So one of the main problems of volcanology is to better understand the volcanic arrest, where an arrest is defined as a deviation from the normal state of a volcano, which may lead to an eruption. An arrest is usually induced by the shallow emplacement of new magma within the shallow magma reservoir, with the new magma which may promote ground deformation, degassing, and seismicity. An arrest can lead to an eruption, otherwise the new magma may stall and the volcano returns to its quiescent stage. Therefore, understanding the nature of an arrest is fundamental for the evaluation of volcanic hazard, and to pursue the same, it is equally important to study both the eruptive and the non-eruptive arrest. Among the restless volcanoes, there are those of the Western Galapagos, which is an hotspot magmatic province making up by 6 active volcanoes with summit mafic calderas, which underwent repeated eruptive and non-eruptive arrests in the last decades, only partially studied. Among these, there is Cerro Azul, even though it is one of the most active volcanoes among those of the Galapagos. Its arrest episodes have been poorly studied. Therefore, we investigated the 2007-2008 arrest, which ended with an eruption divided into eruptive phases. At the beginning, during the first 3 days, there was the opening of the summit eruptive fissures, while in the following 9 days, there was the second eruptive phase characterized by the opening of a distal eruptive fissure. As ground deformation is a constant feature of the arrest episodes occurring in the otherwise poorly monitored Galapagos, we investigated the ground deformation using the synthetic aperture radar interferometry, and in particular, we used a multitemporal approach using the small baseline technique obtained with a combination of ICE and STAMPS software. For this analysis, we processed 83 Envisat images and 38 LOS1 images, generating more than 400 interferograms. And the results showed that in the 7 months before the eruption, there was an inflation of the caldera area. Then, during the first eruptive phase, there was a subsidence close to the caldera, and a complex deformation pattern close to the active eruptive fissures. During the second eruptive phase, there was an enlargement of the subsiding area and a distal uplift close to the active eruptive fissures with the ELOS data, which show that this uplift mainly occurred during the first 4 days of the second eruptive phase. Finally, in the following 3 years, there was a new inflation of the caldera area. To understand which sources caused the observed deformation, we inverted INSAR data for possible magmatic sources. However, the inversion was complicated by the occurrence of unwrapping errors in some of our INSAR data, as it is evident in that zone where we have a lot of fringes, but in the unwrapped data we don't see deformation. So these errors do not allow us to invert for the unwrapped phase as it is usually done, as the unwrapped phase is affected by errors. However, instead of solving these errors, we proposed a new method based on the wrapped phase differences among nearby coherent pixels to model the wrapped phase data directly by estimating the integer ambiguities simultaneously with the model parameters. So we adopted a Markov-chain Monte Carlo method to build a posterior probability of the model conditional to the data, and according to Bayes' theorem, the probability density function of a vector of model parameters given a data vector D is given by this equation, where this is the likelihood function and this is the prior distribution. So we know that for a given discrete inverse geophysical problem, data and model vectors are related by a function G plus an error E. Therefore, to calculate the likelihood function, the probability density function of the error is required, but it is a problem because the multivariate probability density function for correlated wrapped data is difficult to calculate. So we simplified the problem by calculating the phase differences for arcs between coherent nearby pixels, and indeed for coherent pixels, as long as they are nearby, the contribution of the correlated and the uncorrelated noise to the arc phase is small and reasonably approximated by a Gaussian distribution. So thus we approximate the joint probability density function with a multivariate Gaussian distribution with the likelihood function given by this equation, where however now D is the wrapped arc phase values and Q is the variance covariance matrix. So we generated the network of arcs using connecting the nearby coherent pixels using the minimum spanning tree function, which allow us to minimize the length of the arcs. And finally, we estimated the error structure of the data by using a fit variogram function, and then with the nugget seal range, we build the variance covariance matrix where ERH is just the length of the arcs. So we tested this method on both synthetic and natural data, even though now I show you just the results as for SAR Azul. So as for the pre-eruptive inflation, we modeled it with the inflation of a point source placed at 5 kilometers below the caldera floor. Then during the first eruptive phase, we modeled the subsidence with the deflation of a subhorizontal sill-like source placed at the same depth of the previously inflated source, while this deformation pattern has been modeled with a radial dike. As for the second eruptive phase, we again modeled the subsidence with the deflation of a subhorizontal source, while this deformation has been modeled with a radial dike, which constitutes the prosecution of the radial dike of the first event, which turned, changing its strike when it passed propagating from a topographic high to a topographic low. Envisage data show a bad coherence in that zone, while ELOS data show a much better coherence. Anyway, they are characterized by a much worse temporal resolution. However, we can see that the subsidence in the southern flank is lower than that affecting the caldera area. And it is possible to model this deformation pattern using both two deflating subhorizontal sources, which in any case match more or less with the position of the subhorizontal source we used for modeling Envisage data. But it is also possible to obtain the same results by using just one deflating source and the propagation of a deep vertical dike. Therefore, we cannot exclude that there was also the propagation of a vertical dike in the southern zone. So our results suggest that in the 7 months before the eruption, there was the arrival of new magma within the magma reservoir of Serra Azul. Then this new magma was lost by the magma reservoir during the first eruptive phase and was transferred to the radial dike with the opening of the summit eruptive fissures, which were probably just a consequence of the overall upward propagation of magma during this in that area. During the second eruptive phase, much more magma was lost by the magma reservoir and was transferred to the dike, promoting the further lateral propagation of the dike, which triggered the second eruptive phase when it intercepted the topography. And what it is interesting is that the volume of the dike is much higher than the volume lost by the sill. Therefore, it is possible that during this event, the magma reservoir was fed by new deep magma. Otherwise, another explanation was an increase in the compressibility of the magma reservoir, which was almost incompressible during the first eruptive phase, as the volume lost by the reservoir is almost equal to the volume of the dike. And then there was an increase in the compressibility, explaining the volume discrepancies. So, in conclusion, we overcame our unwrapping errors by developing a new method for the geodetic inversions, and thanks to this method, we understood that the two eruptive phases of Serra Azul were mainly related to the propagation of the same radial dike. And thank you.
Thank you, Federico. We're only just on time, so I propose that we move on to our next speaker and then have questions at the end of the session for Federico as well. Thank you.
Thank you.
Okay, you're muted, Virginie.
Sorry for that. So our next speaker is Edna Douale from University of Leeds, and she will talk about radar backscatter analysis of effusive volcanic activity during the 2010-2013 eruptions of Pu'u, Quarter, Kilauea, Hawaii. So Edna?
Yeah, thank you. So you should be able to see my screen now?
Yeah.
Okay,
yep.
Perfect. Yeah, so hi, I'm Edna from the University of Leeds, and I'm going to be talking a bit about using radar backscatter amplitude data to examine an effusive volcanic eruption. So for this case study, we're using the 2010 to 2013 eruption of Kilauea volcano in Hawaii. Here in the background, I have a Sentinel-2 image of the eastern section of the Big Island in Hawaii. And you can see Kilauea summit over here, which for a few months this year actually was housing an active lava lake again. The eastern rift zone, which branches down like this towards the ocean, and a crater here, and its flow field, which is where I'll be concentrating on for this talk. So during 2010 to 2013, this period had three main eruptions that we're focusing on: the Komomo Fissure eruption, episode 60, and the Peace Day flow, all with lava flows that had different characteristics, so it makes it an interesting time to look at. As well, Hawaii is a very well monitored volcano. So we have a good ground-based data set to compare our SAR observations to. So our SAR data set is, we've got a very dense data set, which with just under 300 Cosmos SkyMed, so high resolution SAR images over 2 tracks, an ascending and descending one. And one of the reasons why we wanted to look at radar backscatter is that it has the advantage that it doesn't rely on multiple acquisitions. So you can look at a single image like this and gain an understanding of what is of the ground surface at this point in time, which can be very helpful in an eruption response kind of situation. It also can provide information in areas where we lose coherence. So here we've got a coherence image for the Pearl lava field in 2014. And when a lava flow is emplaced, we lose the coherence. So in this situation, we can't say much from the coherence about the initial lava flow emplacement, especially because this flow actually flowed off into vegetation, which is completely incoherent as well. So, however, if we look at the radar backscatter for the same period of time, if we look at the variation over this 2-year kind of interval, we can see that we actually can pull out the flow in this data set, even in areas where it's gone into the vegetation. So this is one of the reasons we're interested in looking in the radar backscatter, and also trying to understand what information we can gain about the emplacement of the flow, but also the development of the lava flow, especially as this can contribute to the period of time where we lose the coherence, and is also helpful in areas where generally there is an overall low coherence generally low coherence. So just a quick overview of what I mean when I'm talking about radar backscatter. So a single pixel in a SAR image can be expressed by this equation here. Luckily for us, most of these variables are either knowns or constants provided by the satellite. And we're only interested in this one over here, which is the backscatter coefficient and represents the scattering properties of the ground surface. And these properties are controlled by a few factors, which are the gradient of the slope. So if a slope is facing towards a satellite, it'll appear brighter than one facing away. The surface roughness, so a smooth surface will have a lower backscatter than one with a rougher surface, and this is on the scale of the satellite's wavelength. And lastly, the dielectric properties, which is the moisture content of the ground surface, roughly speaking. Right, so if we have now a look at our data. So here I've plotted up the radar backscatter for a single pixel through time, one over vegetation, so over here, and the other one over lava flow. And from first look, we can see the data is very noisy, and there's no obvious signal in either of these. So what we did next is, instead of having a look at a single pixel, we looked at an area, and we find this very repetitive pattern in our data set, which actually coincides perfectly with which of the Cosmos SkyMed satellites actually acquired that image. So it seems like we have quite a strong satellite dependency in this data set. So what we've done to try and correct for this is we've done a principal component analysis. This here showing, this is our first principal component. And if we look a bit closer, you can see that it actually has that same pattern as we saw in the satellite dependency. So we can remove this component from our data set and replot those pixels that I showed you at the beginning. And we can see that the plots have cleared up very nicely. So this one over vegetation is showing now minimal changes in the radar backscatter through time, which is what we'd expect. And the one over the lava flow is actually showing the emplacement of the flow in the radar backscatter quite nicely. So if we have a closer look at these corrected time series for the lava flow emplacement, we can break it into 4 general categories. The pre-lava flow stability level, so where the backscatter remains quite uniform and stable. Then the sudden drop or change in radar backscatter associated with the flow emplacement. The period of time after this, where the backscatter is relatively varied and increasing into what we call the post-lava flow stability level, where it's back to a uniform kind of value. And just to note that this post-lava flow stability doesn't actually have to equal the pre-lava flow stability, because the lava flow completely changes the ground surface, so it doesn't necessarily, well, it won't necessarily have the same values as it had before. So our interpretation of kind of what is happening on the ground surface at this point is the lava flow is in place, and it makes the ground surface quite smooth, which is what we see in that decrease in the radar backscatter. Once it has stopped and starts to cool, it'll form a crust, and this crust will increase the surface roughness over time, which is what we see in this variation bit just after the initial emplacement. So the idea, what we were trying to do is model these different variables and try to say something about not only the emplacement of the lava flow, but also the development through time. So to start off, we will look at the flow emplacement. So the timing, we can calculate the time that this sudden change in the radar backscatter occurs for every pixel in our data set. And we get something that looks like this, where we can plot the appearance of the emplacement of the lava flow through time. So this is the peak day flow. So it's one of the third flow in 2011, which lasted a couple of years. And although we're still picking up a bit of noise, and there are areas where some pixels that we don't know are interacting with the lava aren't being picked up, we can see generally there's a good correlation between the progression of the flow that we've made and the final flow field map, and published flow field maps from the Hawaiian Volcano Observatory and other case studies that look at these flows. What we can also do is plot up the area of that the lava covers for each of the Cosmos SkyMed acquisitions through time. And we get something that looks like this, which is a plot that can tell us something very general about the rate of emplacement at a specific time of the flow, how fast it's spreading at that time, and whether it ever establishes, a very structured system and is not spreading spatially anymore. So if we go back though to our very simple scenario model, so we were just looking at the timing of this bit here. What we wanted to do next is actually look at this recovery, so the time after the first drop and before it reaches the stable level again, and try to. So what we've done here is we try to fit a function to that curve to tell us about how long this period of time happens for each of our pixels. And this was our result from this. From first overview and second, there's not a very distinct or strong pattern that we can observe in this. So either this is telling us that there is no correlation or very low correlation in that recovery time in the radar backscatter pixel, so how fast this goes back to being stable, or that the function we tried fitting to these curves wasn't actually appropriate for our data set. So we've gone back and had a look at our pixels, and we found that it's the pixels show a lot more variability and complexity than we initially had thought. So we can, in a single time series, we can see multiple drops relating to multiple emplacements. We can also see staggered events such as this, and emplacements very close to each other, which would relate to situations where the flow either doesn't cool straight away after the emplacement, but continues developing, producing channels and lava tubes, or where an area where that keeps getting covered by fresh lava and never actually is able to produce a crust and change in the roughness in that sense. And then we also saw that our initial drop, what we would keep saying as an initial drop, can actually be an increase as well. So it's just a sudden change in the radar backscatter associated with the emplacement of the lava flow. And we had a closer look at this. Since we already had all the timings of when these changes happen, we can plot up the magnitude of those changes. And we get this where blue is showing where a pixel is showing a decrease in the radar backscatter associated with that first emplacement of the lava flow, and red is an increase. And generally, very roughly speaking, there's a tendency for a decrease. However, we do see areas such as up here, where the lava flow was emplaced on vegetation, and as well down here on the coastal plain, where there was a lot more variation happening anyway before the eruption. There's a tendency for these increases. So overall, we can see that using radar backscatter, we can produce nice flow field maps and actually look at the progression of these lava flows through time. But we can also, although there's still a bit of work to be done, there's the potential to see a detail in these post-emplacement periods of times, which is especially nice since we lose the currents in this time. So it could be a very nice parallel data set to find something out about that period of time. So for the last few minutes of my presentation, actually, I wanted to talk about something a bit different, which is some of the work we've been doing over the last few months at St. Vincent with Backscatter as well. So just a bit of background, St. Vincent, Soufrière St. Vincent had a dome growing in it at the end of 2020, which grew for about 3 months to heights over 100 meters before it was completely destroyed by the explosive eruption in April this year. So the dome comes out really beautifully in the TerraSAR X images. So this is it here, and you can watch it grow for the 3 months in these images. So what we're doing, and then complete destruction of it afterwards. So what we're trying to do here is look at attempting to calculate the dome growth through time, since this would help us say something about the volume of the dome and the effusive rate in that period of time. So what we initially did was look at the dome and the interaction with the radar shadow. So the radar shadow is formed due to the side-looking nature of the satellite, and has been shown in previous case studies that it can be used to calculate accurate height variations for for volcanic deposits. So this is the trend we got from that. However, due to the fact that we don't have a pre-eruptive TerraSAR X image, we miss out on that initial growth. So all these heights are actually relative to that first image we have where the dome is already present. So they're all relevant to that height. And secondly, due to the shape of the dome, we can't positively say which part of the dome the shadow is interacting with. So it might be, we don't know if it's imaging the highest point of the dome or somewhere off to the side. So these, we can't say are positively the heights of the dome. And especially if we compare them to some of the field heights that were calculated on the ground, we do see there's quite a big shift, although the trend is generally similar-ish. What we're currently trying to we're working on calculating heights from another method, which is using simulated SAR images. So these are some of the very first results we're getting. And these seem to be matching ground-based reports better as well, showing a similar trend, not only to the ground-based observation, but to that radar shadow method, although there is that shift. So this is still work in progress, but hopefully maybe next Fringe will have something more to talk about in this. But that will be it for me. And yeah, thank you for listening.
Thank you very much, Edna. Very nice presentation. Yeah, so I think we will move to the next one.
Right, thank you. So our next speaker is Grace Bato. She's going to talk about the use of SAR and INSAR and source modeling during unrest at Taal in the Philippines. It's all yours, Grace.
Hi everyone. Can you hear me? Okay. So thank you for attending this virtual talk. It's roughly 3:15 a.m. in my time, so please bear with my zombie mode. I will be talking about the Taal volcano and the pre to post January 2020 eruptive crisis based on our analysis of ground deformation from various satellite radar datasets. So this work is actually a result of the crisis response that we initiated last year, and I would like to acknowledge my colleagues or co-authors in this work here: Paul Lundgren, Virginie Pinel, Dr. Renato Solidum, Arturo Daag, and Ms. Maybelline Kahulugan. So this work has recently been published in GRL and it's open access, so feel free to have a look at it or download it. So Taal volcano is a caldera located in the southwestern part of Luzon Island in the Philippines. And as you can see in the figure here, Taal is very close to Metro Manila. It's the country's capital, which is inhabited by roughly 14 million people. Taal volcano ranks as the second most frequently erupting volcano in the country. There were 33 eruptions known between 1572 and 1977. So Taal is part of this what we call as the Macolod Corridor. It's a complex northeast-southwest trending ridge zone. This ridge zone is characterized by extensive active volcanism, crustal thinning, extensive faulting, and block rotation. The recent activities at Taal are actually limited to within the volcano island marked as VI in here. And some people actually mistakenly think that Taal volcano is just this small island here, but in fact, Taal volcano or this volcano island is only part of the entire Taal volcanic region. So this is the whole Taal volcanic region here. The volcanic island or VI here is in fact a resurgent dome within the Taal Lake. It's comprised of 40 volcanic vents. It's the largest is called the main crater. It's the here circular hole in the map. So recently, the geophysical studies at Taal shows that there is this hydrothermal system located at around 2.5 kilometers depth, which is kind of sitting on top of a magma reservoir. And eruption dynamics here are at Taal are mostly controlled by local tectonics and magma reservoir water interactions from external sources that can actually result to different eruption styles and a wide range of explosivity. So on the 12th of January 2020, Taal volcano experienced this phreatic phreatomagmatic eruption after 43 years of repose. The crisis quite evolved rapidly within just a couple of hours, forcing the immediate evacuation of those living within the 14-kilometer radius from the main crater. Civil aviation authorities were also advised to restrict aircrafts flying around the airspace of the Taal volcano during that time. Roughly at around 5:30 p.m. local time, the Taal volcano spewed this column of steam-laden ash reaching up to 15 kilometers high with frequent volcanic lightning, as you can see in this photo here. And the estimated volume of the erupted tephra was roughly 32 million cubic meters. So after this main eruptive phase here on January 12th, Taal's activity began to gradually wane. And in fact, by March 19 of 2020, PVOX downgraded the alert level to 1, indicating a low level of volcanic unrest. And there were roughly 500,000 people that were directly affected by this crisis, with around $69 million worth of damage to infrastructure and agriculture that has been reported. So when Taal erupted, I was obviously still sleeping here in LA. There is a 16-hour difference between LA and Manila. And so when I woke up with a lot of text messages from friends and family back home. And in fact, my parents live really close to the volcano, so I was quite worried during that time. But my immediate reaction, I guess, as a very INSAR enthusiast, I would say, was to check available SAR data. I also texted or asked Dr. Paul Lundgren if we can acquire ALUS2 data during the time covering Taal while I process some short-term Sentinel-1 datasets. And all the analysis, the datasets, and all the interpretations that we produced during the time were directly communicated to the local observatory, FIVOX, in near real time to support them during the local crisis. And here in this slide, as you can see, is one of the first pre-eruptive ALUS2 INSAR data that Paul produced. This data was from the Ascending Pass. It covered 10 months of deformation between January 2019 and November 2019. And here you can see that there is roughly one distinct fringe pattern within the volcano island. So this is another ALUS2 INSAR data, but this is from the Descending Pass. Here you can see roughly 2 sets of fringe within the volcano island. Because unlike the previous image, this data set covers roughly 1 year of deformation from January 13, 2019 to January 12, 2020, few hours just before the eruption. And interestingly, the Sentinel-1 data set, which covered 12 days prior to the eruption, did not show any significant or noticeable deformation, as you can see in this figure. Supposedly, the next planned acquisition over Taal was on the 21st of January 2020. But we thought to further help the observatory, we could ask ESA through the Sentinel-1 mission manager, Mr. Pierre Potang, to acquire Sentinel-1 data at 6-day intervals for both the ascending and descending tracks in the next few cycles. And fortunately, ESA granted the request until February 2020, so we were able to image the eruptive event quite quickly. I will show that later on. So while we were anxiously waiting for the first SAR acquisition that would allow us to produce that co-eruptive interferogram, we thought we can use first the ALUS2 data sets and at that time and model the pre-eruptive source of deformation. So we use the compound dislocation model or CDM module in our in-house Bayesian software called Alter. And Alter is this software based on the cascading adaptive transitional metropolis in parallel, or CATMIP, developed by Sarah Minson. It was initially developed at Caltech to model faults, but it has now been extended to model volcanic sources, both kinematic and simple conduit dynamic models. So Alter combines simulated annealing and metropolis sampling, and it is designed to sample high-dimensional problems to run in parallel using HPC. So modeling our quad-feed dataset using Alter was very quick. It only took us a couple of hours in my local machine, and we found that there's this northeast-southwest striking ellipsoidal body, which is located east of the volcano island at roughly 4 kilometers depth. And this slide that you can see here, this is the exact one of the exact slide that we sent to FIVOX during the peak of the crisis. So when the crisis was over and we had more time to explore more data sets and improve our model, we generated a time series of deformation starting around late 2014 using available Sentinel-1 and ALUS2 data. We also activated JPL's ARIA processing system, and ARIA produced these thousands of Sentinel-1 interferograms in no time. So we then used MinPy to produce all the deformation time series. Left image here is an example of cumulative deformation map from Sentinel-1, descending track 32, covering Taal until January 9, 2020. And the right image shows the deformation time series plot from Sentinel-1 and ALUS2 datasets. And here from the plot, we observe a long-term deflation period followed by a short-term inflation period prior to Taal's January 2020 eruption. We found that this observation is actually consistent with GPS measurements at Taal. So we took the velocity within 1 year of the inflation, and then we modeled the pre-eruptive deformation source, again using the CDM module in Alter. And we find that this, again, northeast-southwest trending ellipsoidal body, but instead of 4 kilometer depth, we found a deeper source, which is roughly 5 kilometers beneath the volcano island. And this depth is actually more consistent with previous studies at all using GPS and seismic data, although those previous works have modeled the deformation as a point source pressure. So just for visualization purposes, this is the ellipsoidal source beneath the volcano island, and we estimated that the volume of this source is roughly 45 million cubic meters, or roughly 18,000 kind of Olympic-sized swimming pools. So going back to the crisis response story on January 15, the Sentinel-1 in its descending orbit was scheduled to acquire the data over Tal, and this acquisition was very important because this would allow us to produce the first co-eruptive deformation map, and this will also allow us to assess and have a better understanding of the current volcanic state. The in-situ measurements in the volcanic island during that time have either stopped or temporarily really stopped operating, and it was very difficult to assess the volcano island because of the plume. So during the time, people only rely on the measurements and data from stations around the volcano and from the larger Philippine National Seismic Network. This image that you can see here, this is the first co-eruptive interferogram at all January 2020, captured by the Sentinel satellite. We produced this at around late afternoon of of January 15 LA time, and this shows the extent of how much the ground deformed due to the eruption. For Sentinel, each set of fringe corresponds to 2.8 centimeters of ground deformation within the volcano island, and on the Pansipit River Valley here, you can see that the deformation are so large that fringes become dense, so they alias. So what we did is, instead of the phase, we analyzed the amplitude component of the radar data. We were able to produce the map on the right, and the method is called pixel offset tracking. And using pixel offset, we can better measure those areas where fringes are dense and are hard to separate from each other. And here you can see even the red pixels in the main crater of the volcano island, and these are actually emplaced volcanic deposits. Also, you can see that there's a sharp difference here in the direction of the displacement in the Pansipit River Valley. So we interpreted the signal from this co-eruptive INSAR and pixel offset map as a result of the emplacement of a large dike and the deflation of a magma reservoir. So this initial interpretation during the ongoing crisis was further supported by subsequent ascending interferogram covering the ground deformation between January 11 and January 17. Observed fissure locations that appeared at Tal also corroborated our data and our analysis. This is the map provided by PHIVOX. These are like locations of the fissures that appeared within the region of Tal. So using the phase maps and the pixel offset map, we modeled the co-eruptive source of deformation, and we found that the magma reservoir actually lost a volume of roughly 531 million cubic meters, while 643 million cubic meter of volume of dike is laterally emplaced. So when we sent this information to PHIVOX, we mentioned that if 50% of the dike volume were actually erupted explosively at that time, it could have been a VI for eruption. So when the activity waned, we were able to perform more sophisticated modeling, and we did some distributed dike model. And here the model indicated strong opening below the volcano island that extended southwestward toward the Pansipit River Valley at roughly less than 10 kilometers depth. And although the strongest opening that you can see here is around or just beneath the Taal Lake, it is still unclear if the dike reached the bottom of the lake. The lake has a maximum depth of roughly 198 meters. So subsequent to the main eruptive phase, we found persistent surface deformation at Taal. The volcano island continued to deflate of up to 0.8 meters until around February 4 of 2020, before inflation signals are again detected. So here the left figure shows INSAR measurements from January 15, 2020 to March 16, 2021, and right figure actually shows GPS measurements covering almost the same period. So right now, alert level at Taal has been raised from abnormal condition to increased unrest since March 9 of 2021 due to, again, elevated unrest in the region. But for official and regular volcano updates at Taal, please visit the PHIVOX official website or follow their social media accounts. The Volcano Observatory reminds the public that alert level 2 can result to steam-driven or phreatic explosions, volcanic earthquakes or ashfall, and even lethal accumulations or expulsions of volcanic gas within the threatened areas. So just to summarize this talk, prior to the eruption, we saw that there is a long-term deflation followed by a short-term inflation period, reflecting possibly the pressurization of the 5-kilometer deep magma reservoir at Tal. It's a northeast southwest trending ellipsoidal magma reservoir. What is interesting with the pre-erupted data set at Tal, the sequence of deflation and inflation were actually accompanied by a decreasing trend in CO2 flux measurements within the main crater lake from 2015, and then also a rapid increase in CO2 flux in the beginning of 2019, as reported by Bernard et al. In this figure here. During the eruption, the magma reservoir lost a volume of 531 million cubic meters, while a 64 million cubic meter lateral diet was in place. And after that, our post main eruptive phase analysis showed that the magma reservoir started inflating again 3 weeks after the January 12 event. I do not have enough time to explain this, but these are the lessons learned that we had during the crisis, and thank you very much.
Okay, thank you, Grace. I think we will just move to the last talk, so which will be given by Susanna Ebmeyer. So she will give us an overview of the CEOS demonstrator for Latin America, Southeast Asia, and Africa.
Thank you, Virginie. I will start off by saying I realize it's not ideal to give a talk in a session that you're also co-chairing, but I hope you'll forgive me in this, because what I'm talking about just now isn't really representing just my work, but the work of a much broader group of people, including many volcanology researchers at universities, researchers at volcano observatories, and people who work at space agencies as well. I'd also like to say that this is preliminary results, so there's a focus in this talk on volcano monitoring rather than a kind of final research analysis for some of our examples. So some of the results are really very, very early, and we expect that they'll develop in the next few years. So I'm going to use this time to describe what the CEOS volcano demonstrator is. So it's the Committee for Earth Observation Satellites Working Group on Disasters Volcano Demonstrator Program, which is quite a mouthful of a name. But I'll go into what our motivation are, what our aims are, and the activities that we're currently doing. That's going to involve some discussion of background tasking, so trying to make sure that we have the most useful imagery that we can during a volcanic crisis or eruption. And I'm going to also summarize response to eruptions over the last couple of years and some emerging themes. So these are going to be the implications of automated processing, primarily of Sentinel-1 imagery, and perhaps we can anticipate the automated processing of NISAR imagery when that comes online. The importance of a constellation approach to SAR imagery and INSAR in volcanology in particular. And I'm going to touch briefly on commercial SAR instruments for volcanology and where they might be important and useful. I'll finish off with some take-home messages about the demonstrator project, and also some potential themes for seed questions, which is how we can use the last 15 minutes of this session, as well as allowing all of the speakers to address the questions that have come in through the chat. So the Volcano Demonstrator is an extension of the Latin American pilot project, which ran from 2013 to 2017 and is summarized in an article by Matt Pritchard. It was published in 2018. That focused on trying to get a diversity of SAR data and in-SAR processing to volcano observatories in Latin America, filling in any gaps in monitoring and trying to maximize the way that we use these data sets. So the extension of the demonstrator is to extend that geographically, so no longer focusing just on Latin America, but also in the volcanically active parts of Africa and in parts of Southeast Asia. We started in 2019 and expect to run for at least 3 years. And our kind of long-term goal as a project is to demonstrate that it's necessary and also possible to coordinate satellite tasking for volcano monitoring. And it's something that we should aim for as a community. It's something that the polar science community already does. And this is an attempt to demonstrate this is something that we should and can do. So the kind of general goals for the demonstrator project are to expand the use of satellite remote sensing for volcano monitoring, to support and do research between the links between volcanic unrest and eruption using satellite observables. So that really refers to integrating the SAR measurements and in-SAR measurements with thermal and degassing measurements as well. The international coordination of satellite tasking I've already mentioned, and also supporting capacity building initiatives in volcano observatories. So to kind of condense that down to kind of 2 more pragmatic descriptors of what we do. So at the moment we're focusing on use of diverse wavelengths because Sentinel-1 imagery are widely available, freely available, and there's automated processing on offer. What we're trying to do is make sure that the less accessible data sets get to the right people during volcanic crises and contribute to volcano monitoring. So in practice at the moment, that primarily means supplementing C-band imagery with X-band. And also supporting or collaborating with volcano observatories. And that means a big range of different things for different parts of the world. So in some places, it means playing a small role in tasking imagery, coordinating acquisitions. In others, it means helping with some data processing, doing some analysis or modeling, and also collaborative research. So our activities kind of spread on a spectrum between those 2 ends. So the imagery quarters that we're working with at the moment are Cosmos SkyMed from ASI, TerraSAR X from DLR, Pleiad imagery from CNES, and we've also had some ad hoc imagery provided during periods of volcanic unrest and eruption from INTA, from CONAI, and from ISI. I'm going to start off by showing a few summary figures to give you an idea of where the project is working. So the numbers after the countries named on this figure show the number of volcanoes where we're tasking TerraSAR X imagery as essentially to try and get a baseline so that if there is an event at some point, we're going to have some pre-event imagery in order to make interferograms. I think this is quite an important thing to do, and it's also challenging to try and anticipate where the next events are likely to be and also how long coherence can be maintained. So if people have input into this or suggestions of places that we should be tasking TerraSAR X imagery, but we aren't, they'd be very welcome. I also wanted to say that we have a lot of presentations from Instituto Geofísico in Ecuador during the poster session for this session at Fringe. And some of these are using CEOS volcano demonstrator data, particularly at the volcanoes of Chiles Cerro Negro, Sangay, and at El Reventador. So if you'd like to check out those posters. Pleiad imagery so far we've acquired or requested primarily over volcanoes in Latin America, and the particularly exciting result from this last couple of years is from Nevadas de Chillán, where it's been used to produce different digital elevation models showing the progression of lava flow emplacement over the volcano, and allowed some estimations of a fusion rate. And over the last couple of years, we've also responded to several eruptions. I'm going to talk about these in a little bit more detail just now and give you a look at some of the interferograms from Merapi and Sinabung, and also St. Vincent. So starting off with Merapi, the interferogram on the right is the Cosmos SkyMed spotlight image from October the 5th to the 13th of last year. Merapi started showing signs of unrest in late 2020, and the local deformation monitoring consists of an electronic distance meter line on the west flank of the volcano and GNSS network. The challenge with that network is that a lot of it is quite distal from the volcano summit itself for obvious reasons. Instruments are likely to be destroyed in frequent eruptions. And high-resolution X-band data proved to be extremely useful in responding to this event in assessing complex deformation patterns that were taking place very close to the Volcanoes summit. If I remove the amplitude there, you can see the complexity of the displacements on the western flank of Merapi there. These interferograms are from Mike Poland at the USGS. So moving through to November, this is a staring spotlight TerraStar X image. And if I again remove the amplitude, you can see the very high fringe rates here, just on the edge of the region of coherence, showing small scale but very rapid displacements across the western flank of the volcano. And this is something that Mark Bemelmans at the University of Bristol has also been looking at with pixel offset tracking, which gets around part of the issue of the poor coherence close to the volcano summit. So the eruption finally began in January 2021, and the value of the X-band satellite data to CVGHM is largely that it was able to demonstrate that these rapid displacements were taking place near the summit, and also that they had ceased in January. During this event, we also had some imagery provided by SAR and PAZ, and that included a pair that allowed a combination of TSS and PAZ, increasing the number of acquisitions and decreasing the time span of the interferograms. So that was a pretty cool thing. Looking at Cinnabon, what's really been useful here has actually been the backscatter and the amplitude imagery, particularly in mapping changes in the lava flow and lava dome and in flow activity. The particular value for the volcano observatory here was in giving some indication that the flow is becoming unstable, because flows becoming unstable has been what has been implicated in beginning of hazardous pyroclastic density flows at Cinnabon in the past. And you can see the scale of the 2020 activity in the animation here. So Edna in her presentation already mentioned St. Vincent. One of the things that was really critical, I think, in the response to the St. Vincent's eruption, that involved a lot of different people through the CEOS Volcano Demonstrator and through other collaborations with the University of West Indies and Seismic Research Centre and other universities, was that we had a real diversity of different satellite instruments providing imagery, and that really allows quite a good picture of the growth of the dome, particularly from the beginning of 2021 onwards. So this figure, which was put together by Edna, shows the growth of the dome, which she already showed in animation, but it highlights how different it looks in the different geometries and the amount of information that you can get by combining them instead of just by using one. It includes an eyesight image on the right. And just as an aside, I know that Mingjong Zhou's poster talks about the ALOS data in the period running up to the eruption at St. Vincent, which is quite a different part of the story. So one of the nice things about the backscatter imagery here is that it gives a very detailed picture of the dome growth in an area where INSAR isn't really possible because the coherence was so poor. And I think that scientists at the University of the West Indies found it incredibly useful, as it was able to fill in some gaps in their time series from overflights and photogrammetry. So moving away from event response and into some more kind of in-depth research of recent events. So this is a couple of figures from Mark Bemelmans at the University of Bristol, who's working with Juliette Biggs there. And he's doing some reanalysis, I guess, really, of the Agung eruption in 2017. So there have already been articles published about that eruption that describe the larger scale displacements. But Mark is really focusing on the displacements that took place only within Agung's crater itself. So relatively small, about 5 kilometers across. And you can see the combination of the Cosmos SkyMed imagery and TerraStar X imagery on the left there that capture very high fringe rate displacements only within the crater. And of course, that would be displacements that we would attribute to quite different sorts of mechanisms than the broader scale deformation. You can see one of Mark's initial interpretations in the figure on the right, which shows the best fit rate of displacement and also labels a topographic artifact there, so that he's demonstrated that displacement is limited to the crater floor itself. Something else that's come out of the current phase of the volcano demonstrator is Edna's paper looking at Fuego eruption in 2018. I think the nice result from this is that it's a demonstration of how you can use Backscatter to look at eruptive products, which is pretty challenging. But rather than just looking at the emplacement of pyroclastic flows, for example, she spent some time looking at all of the possible backscatter combinations between sets of images acquired over the period when Fuego erupted in 2018, which allow her to distinguish between various different processes like pyroclastic flow emplacement and then removal due to erosion, lahars, and major rainfall events. And this has been pretty successful in capturing the events that were also reported by the observatory in Zuvume during the same period. So moving now to kind of a general overview, some emerging themes that kind of come out of trying to work on this sort of volcano monitoring problem at the moment are the implications of automatic processing. And I'm mostly talking about automatic processing of Sentinel-1 imagery at the moment. There are lots of different groups working on this, and there have been a lot of other presentations at Fringe that deal with this particular issue. There's quite a lot of possibilities for doing on-demand processing. The example that I'm showing on the left here is the result from automatic processing through the Comet LIXAR system, which I'm using as an example because I'm more familiar with it, with some time series produced by our automatic web tools on the left. So that is for Shanghai in Ecuador. And you can see the uplift taking place there over the last 4 years. So the nice thing about automatically detected unrest and automatic processing is that it frees up time for analysis, and it's certainly the best sort of approach for regional monitoring and for searching for unrest that you don't know about, so unknown unknowns, so to speak. And it does mean that the work within the volcano demonstrator in this phase has really focused particularly on episodes of unrest and eruption where we can supplement what's already possible with C-band data rather than on broad surveys. The other theme that I want to mention is that it really does make a difference to have access to multiple satellites at the moment. 12 days or 6 days is not necessarily enough to capture the important changes at a volcano, which we need to know about in order to forecast hazard or to think about how an eruption might progress. Unrest and eruption can happen quickly, they can change within hours to days, and the sooner the images can be acquired, the better. So access to imagery from multiple platforms increases the likelihood that we can capture multiple events, and denser time series also allow more interesting and useful retrospective analyses. I'm just going to illustrate that with an example from Anak Krakatau in 2018. There was a Sentinel image acquired on the same day as the eruption, but there was some ambiguity in how to interpret it. It's a little bit challenging at the lower resolution, but a Cosmos Skymed image acquired the next day really allows us to look at the shape of the new island, and that image itself is important for constraining the sliding slope and the total landslide volume of the collapse during this failure event. But more than that, the use of multiple SAR satellites really allowed the time series of the change in the shape of the island to be densified and allows a much more detailed analysis. So,
Susie,
yeah,
maybe you should conclude soon if we want to save time from the discussion.
Apologies. The last slide here shows Ice Eye and Capella imagery acquired and contributed to the CEOS project. I will move to the end, which were seed questions and emerging issues. And let's move to the discussion.
Thank you. So you let us with the seed questions. Yeah. Yeah, I'm not sure how to proceed. Maybe there are already some questions in the chat, so we can start with the question and then come back to the seed questions if we have time. So there were some questions for Paul. Paul, are you still here? Yeah. So
still here.
there are two questions, one on the observation, the signal, and another one on the modeling and the volume estimation. So for the first ones, so it is since the inflation period, have there been any local small footprint deformation signals associated with the hydrothermal activity?
Nothing that I mean, the interferograms don't show anything more detailed than just the broad scale deformation. Although we don't have any, I don't know if there's been any change in the hydrothermal activity. Back in the, I think around in, I can't remember the dates exactly, it's like 2009, and during a previous period in which the thermal time series went up, there were some kind of small hydrothermal explosive, very tiny explosive activity in the hydrothermal field. So there was, Tarsilo has interpreted that as corresponding to increased thermal, flux, thermal activity there. So.
Okay, thanks. And the next one was about the volume estimation. So it is the shape of your best CDM model is still like, but how is the volume change distributed among the 3 CDM planes, if independent?
Yeah, so the CDM solution of MEDI is all of the planes have a uniform. I mean, the solution itself is represented by 3 dislocations, tensile dislocations, and each has the same opening, and from that you compute the volume change of the source. So yeah, it's always uniform.
Okay, so no, you have no insight on the ratio between the contribution of the vertical planes, but mostly it's horizontal in this case, right?
Well, I mean, the solution, the analytical solution is a representation of roughly of an ellipsoid. Of course, as it gets closer to the surface, there can be, and depending on the aspect ratio, there is a depth that, based on the finite size at which it starts to become, less accurate compared to what a true volume source, say from a boundary element or finite element solution, would give you. But yeah, the solution is approximately that of an ellipsoid. So it's the volume change. Think of that as equivalent to the same size ellipsoid, what the pressure change would be to give you that same kind of volume change. So in other words, it's uniform. It's not something non-uniform.
Okay, thank you, Paul. There is also a question for Edna, and is it, how do strong rainfall events affect your amplitude image analysis at Kilauea?
Yeah, so at Kilauea itself, we haven't seen any strong variations in the backscatter associated with rainfall, which I guess, I don't know, it might have to do with, at the moment, the flows we're looking at are all on that low field, and not much interaction with the vegetation, where I think we would see a bit more. And the fact that the emplacement has a large variation in the backscatter, so would overshadow some of it. But it's definitely something we do consider and have a look at, because we've had other case studies at tropical volcanoes where we've seen quite a strong effect of the rainfall. But yeah, Kilauea, not really at the moment.
Okay, maybe I would have another one for you. It's about the recovery time you have in the backscatter change. So so there is no clear, I think you haven't found any clear link with any real physical meaning. Maybe I'm not sure, but I would say my question is, could there be a link with the thickness of the flow, or I mean, could the recovery time be linked somehow to the thickness of the flow and blast?
Yeah, quite possibly. So it's something we're still working on looking at, because we're just trying to understand all the possibilities, because the flow can be quite complex in it doesn't just get in place and cool, but a lot of things do happen. So trying to see, it's probably fitting one very simplistic model is not the way to go about doing it. So it's trying to figure out exactly how we can have a look at that recovery time and actually quantify it or explain it in a bit better way at the moment. So yeah, it's something we want to look into as well a bit more. That makes
Okay. Yeah, there's another one for you. Did you estimate the uncertainty is in Backscatter change? Also, not sure if you use multi-look pixel, and in this case, do you expect signal over noise to be correlated over what spatial scales? So,
so we do apply a kind of a boxcar situation to the data set when we do that PCA correction. So that is, I guess, similar to the multi-looking where you smooth it out a bit. But we haven't done a proper estimation on the uncertainty of the changes at the moment, but that probably should be something we will look into and do properly further on in this work.
Okay, thank you. So maybe we should now try to discuss the seed questions and to prepare the technical session, which will be tomorrow at 4 p.m. And you are all invited to join this session. So I will let
today
Susanna.
the technical session. So today.
Yeah.
Yeah. So I came up with some kind of straw man ideas for seed questions for the technical session, but it would be great to get your feedback on what you think the questions are that we should be discussing. So to go through them very quickly, I suggested that I know on Monday there was some discussion of Sentinel-C launching, and I thought an interesting question for our community would be, under what conditions might it be switched on? For example, during a volcanic crisis, would it potentially give us denser time series? I thought other potentially interesting topics for discussion were the use of commercial SAR imagery in volcanology, automated processing, and the constellation SAR that was discussed in the CEOS talk at the end. But if anyone has feedback or anything they'd like to add, or any questions they think are not worth discussing, please let us know, and we'll try and put these together before the technical session tonight. I see there's actually another question that's come in just now for Federico, and that is, what's the difference between your modeling approach based on unwrapped data and the one called WGBIS by Jiang and Gonzalez? That's quite a specific question. I think you're muted.
Okay. To be honest, I don't know the model by Gonzalez at all. Therefore, it's a little bit difficult to answer to this question. However, the fact is that my model is based on the wrapped phase differences among nearby coherent pixels. So therefore, if you have any unwrapping errors and you don't want to solve this, but you want to model your data, you can model this unwrapping phase affected by errors and find the true solution. Because instead of inverting for the unwrapped phase, I inverted for the phase differences among nearby coherent pixels. Therefore, I don't need to solve this error to obtaining the solution. So I don't know if I answered to the question, but yeah, unfortunately, I don't know this method proposed by Gonzalez et al. So,
and perhaps it's one for further discussion offline.
Yeah. Anyway, I published this method. Therefore, for any further consideration, you can read the article if you are interested.
So I'd like to say thank you again to all of the speakers in this session. We had a set of really nice talks and covering quite a wide range of topics, I think, for such a short session. And please do give us some feedback on seed questions or any other things that you'd like to be raised in the technical session this afternoon. And otherwise, we'll see you at the poster session.
Okay.